the 2020 Fryer contest. Question 3 reads, in a d-lin sequence, the first term is a positive integer, and each term after the first is calculated by adding 1 to the previous term in the sequence, then doubling the result. For example, the first 7 terms of the d-lin sequence with first term 4 are 4, 10, 22, 46, 94, 190, and 382. Part A reads, the fifth term in a d-lin sequence is 142. What are the fourth and sixth terms in the sequence? So to start off, just for our easier notation, let's call the ith term d sub I, or di. Now for the fourth term, let's apply the definition of the sequence. We have that every term is the previous term plus 1, then multiplied by 2. So applying this to the fifth term, we should have d5 equal to 2 times d4 plus 1, and then times 2 here. Here I'm just applying the definition. d4 plus 1 times 2 should give me d5. Now we know that d5 is 142 as given in the question. So let's substitute in 142 into this equation here. And we'll get an equation in one variable, namely d4. So we have 142 equals to 2 times quantity d4 plus 1. Now let's divide both sides by 2. So we're left with 71 on the left, and on the right we have d4 plus 1. And finally, let's subtract 1 from both sides, leaving us with d4 equals to 70. Similarly, for the sixth term, let's again apply the definition of the sequence. We have that d6, the sixth term, by definition is the fifth term plus 1, and then times 2. So substituting the value that we know for d5 is 142, we have that d6 equals 2 times quantity 142 plus 1. And evaluating the right-hand side, we should have 142 plus 1 is 143, and then times 2 is 286. So d6 is 286. Part B reads, determine all possible first terms which give a d-lin sequence that includes 1406. So let's start with what we know. The question tells us that for any given term in this sequence, we can find the next term by adding 1 to the current term and then multiplying by 2. In other words, let's write down for any given di, a term that we have, we can find di plus 1, which is the next term, by calculating 2 times quantity of di plus 1, like so. This tells us that if we have any given term, we can always find the next term. This means that we can go forward in the sequence. We can always find the next terms in the sequence. Now similarly, let's figure out how we can go backwards in the sequence as well too. If we're given a specific term, let's derive how we can find the previous term. So in this case, now we're trying to find a di minus 1 given a di. So let's write down the relationship that we know between these two terms. Well, we know that di is the next term in the sequence of di minus 1. So we can write down that di is actually equal to 2 times quantity of di minus 1 plus 1. And this again is just applying the definition of this sequence to find the next term. Now we have an equation in di and di minus 1. Let's isolate for di minus 1. We do so by dividing both sides by 2 first, so we have di over 2, and that's equal to di minus 1 plus 1. And lastly, let's subtract 1 from both sides. So we have that di minus 1 is equal to di over 2 minus 1. With this, now we have the ability to go backwards in the sequence. So given a current term, we can find the previous term. Now let's use this to solve for what the question is asking us. So the question tells us that there is a term in the sequence which is 1406. So we need to find how many such sequences there are that includes this term. So let's see what happens if we set some terms to be 1406. First up, if d1 is 1406, this is a valid sequence because we can calculate all the future terms in this sequence. Now let's try if d2, the second term, is 1406. Well, what would be the first term of this sequence then? We can apply what we derived earlier to find the previous term. with d1 is equal to d2 over 2 minus 1. And calculating that out, we have 1406 divided by 2 minus 1, which is 702. And this again is a valid d-lin sequence. Similarly, let's see if d3 is 1406. Then to find the previous term, we again apply what we derived above. Now, this time, we have that a given term is 1406. The previous term is 702 because we already calculated in the line above here, where we have the one term is 1406 and the previous term was 702. So in this case, we know that the d2 would be 702. And similarly, d1, again, applying what we derived above to find the previous term, we have that d1 is 702 divided by 2 minus 1 is equal to 350. And this again is a valid d-lin sequence. Similarly, we'll do the same thing for d4, d5, and d6. Let's suppose d4 is 1406, then d3 is 702 because that's the previous term, d2 is 350 because that's the previous term as calculated in the line above, and finally d1 is 350 divided by 2 minus 1 by applying what we derived before. And this gets us that d1 is 174. This again is another valid d-lin sequence. And we can see we can apply the similar process again and again to see when we can hit an issue. So d5 is 1406, d4 is 702, d3 is 350, d2 is 174. All of these are calculated above. And finally, d1 in this case will be 174 divided by 2 minus 1, which is 86. And this again is a valid d-lin sequence. Similarly, d6 is 1406, then d5 is 702, d4 is 350, d3 is 174, d2 is 86, and finally d1 will be 86 divided by 2 minus 1, which is 42. And this again is a valid d-lin sequence. Now we see, but at this point, that there's a pattern here. And the pattern is each time we only really need to calculate the one new term. Like in this case for d6, we calculate the d1 is just the last term that we had before, and then applying what we derived above to find the previous term. So we can do this for d7 and save some writing here. If we have d7 is 1406, then d1 will be the previous d1, which is 42, divided by 2 minus 1, and that's 20, which again is a valid d-lin sequence. And continuing this on, we have d8 is 1406, then d1 in this sequence will be 20 divided by 2 minus 1, which is 9, and that's valid. Lastly, if we try d9 is 1406, then we get d1 is the previous calculated number 9 divided by 2 minus 1. And here we see we have an issue because 9 divided by 2 minus 1 is no longer an integer. And the question tells us that the first term and every term in the d-lin sequence should be an integer. So in this case, this is no longer a valid d-lin sequence. Now, how do we know that that's all of the possible d-lin sequences that have the term 1406? Well, we know that because if there's some other di, let's say for some bigger number, d100, let's say, is equal to 1406, well then one of the earlier terms will no longer be an integer. Just like how we showed for d9, because at some point down the line, one of the terms will end up being 9 over 2 minus 1, which is no longer a valid term of the sequence. And this tells us that no further di past 9 can be a valid d-lin sequence that has a 1406 as a term. So therefore, there are only 8 d-lin sequences that include 1406 as a term. And the first terms for these sequences are exactly the values that we calculated out, namely 9, 20, 42, 86, 174, 350, 702, and 1406. Part C reads, which possible first terms from 10 to 19 inclusive produce a d-lin sequence in which all terms after the first have the same ones or units digit? So for this question, we're actually trying to find all the d-lin sequences that start with 10 to 19, which from the second term onwards all have the same ones digit. For this, let's take a look at two different approaches. The first approach will be a trial and error approach. Because we're looking for a sequence with the second term onwards all have the same ones digit, let's go ahead and compute all the second terms for which the first term is from 10 through 19. So let's draw a table like this. And we have here that the first terms, 10 through 19, across the top here. So we have 10, 11, for example, all the way through till 19. Now let's compute the second term, knowing our formula for the first term, which is 2 times the first term plus 1. So 2 times 10 plus 1 is 2 times 11, which is 22. Similarly, 2 times 11 plus 1, which is 2 times 12, is 24. And following this, we can compute the second term for all of the terms here, and we get something like this. 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. Now, we need to know that from the second term onwards, all the terms have the same ones digit. So let's take a look at the third term then. To compute the third term, we need to take the second term and again apply what's given in the question to find the next term. So for the second term of 22, the third term will be 2 times 22 plus 1, which is 2 times 23, which leaves us with 46. Similarly, for a second term of 24, the third term will be 2 times 24 plus 1, which is 2 times 25, giving us 50. And again, we'll go ahead and follow that pattern for the rest of the possible second terms. So we'll end up with the results 54, 58, 62, 66, 70, 74, 78, and 82. Now, we know we're looking for sequences where the ones digit of the second term onwards is all the same. So comparing the second and third term for each of these here, we see that, for example, for a second term of 22 and a third term of 46, they don't have the same ones digit. So this is not a sequence that we're looking for. Similarly, for a second term of 24 and a third term of 50, again, they don't have the same ones digit. So this is not a sequence that we're looking for. Looking through all of these, we see that only this second term of 28, a third term of 58, as well as a second term of 38 and a third term of 78, these two sequences have the same ones digit for at least the second and the third term. Now at this point, in this approach for the trial and error, we can just go ahead and guess that these two sequences will continue to follow this pattern because it's followed it here. Now, of course, this is not a very rigid or rigorous approach. So let's actually look at the next approach, which will be more rigorous. In this second approach, we'll take a look at using modular arithmetic to solve this problem, which will result in a more rigorous solution. So first, let's make an observation that an integer can be written as 10k plus d, where k is an integer and d is a digit. And by digit, I just mean it's an integer between 0 and 9 inclusive. Now let's take a look at some examples to illustrate what I mean. For example, if I have 17, which is an integer, I can rewrite that as 10 times 1 plus 7. Similarly, if I have 26, I can write that as 10 times 2 plus 6. Here we are basically isolating for the last digit here. That's the intuition behind writing the integer in this format. Now, suppose I have a term in a d-lin sequence, di, and I'll rewrite that as 10k plus d for some k and d. Now let's try to find the next term, or di plus 1, using this. So we know that di plus 1, by applying the definition of the sequence, is equal to 2 times quantity of di plus 1. And in this case, that would be 2 times quantity of 10k plus d plus 1. And expanding that will result in 20k plus 2d plus 2. Here, we need to make another important observation, and that's that the units digit of a number is always the remainder when that number is divided by 10. Or in other words, we call that mod 10. Here, mod 10 just simply means the remainder when divided by 10. So what we are actually looking for is that di mod 10 is equal to di plus 1 mod 10, where I is at least 2. Because in the question we're looking for from the second term onwards, the units digit will always be the same going forward. Now let's substitute in our notation in k and d for di. So for example, we have 10k plus d, which is di, mod 10, equal to 20k plus 2d plus 2 mod 10. Here in mod 10, we see that 10k will always be divisible by 10, so the remainder will always be 0. So on the left-hand side, we're left with just d mod 10. Similarly, on the right-hand side, we see that 20k is always divisible by 10, so the remainder will be 0. That means on the right-hand side will turn into 2d plus 2 mod 10. From here, we see that this is an equation that only depends on d, and we said that d earlier is a digit, meaning it's a digit from, it's an integer from 0 to 9 inclusive. So now we can draw a table of the values for d. We know that all the possible values for d are from 0 to 9. And let's compute d mod 10 and 2d plus 2 mod 10. And here, because d is a digit, we see that d mod 10 is just d, so it's the numbers from 0 to 9. Now let's compute 2d plus 2 mod 10 for each of these units digits. So, for example, if d equals 0, then 2d plus 2 mod 10 is 2. Similarly, if d equals 1, 2d plus 2 mod 10 is 4. Let's take a look at a more interesting case. For example, if d equals 7, then 2d plus 2 mod 10 is actually 16 mod 10, which is 6. And we do that same calculation for all the digits, and we have these numbers in the second row of this table here. Now, observe that only the digits 8 will continue to have the same units digit in this sequence, because we need to know that for any units digit, we need that units digit times 2 plus 2 to also have the same result mod 10. And we observe here that only the digit 8 here, as we see here, units 8 has the same value in d mod 10 and 2d plus 2 mod 10. Meaning that only when the second term of a d-length sequence ends in an 8, then we know that that d-length sequence will have the same units digit from the second term onwards. Now, we can reuse our work from the first approach, which calculated all of our second terms here, and observe that for the second term to end in 8, we only have 28 and 38. Meaning that only the first terms of 13 and 18 will have such sequence where the second term onwards will all have the same units digit going forward. And so we can conclude then that there are only two possible first terms, namely 13 and 18, that will have second terms that have units digit 8. And those are the only two sequences which will have the property asked for in the question. Part D reads, determine the number of positive integers between 1 and 2020 inclusive that can be the third term in a d-length sequence. For this, let's start off by supposing the first term is called k. Then let's try to find the second term. And we just do that by applying the definition of the sequence. And we know that the second term is 2 times the first term plus 1, so 2 times quantity of k plus 1. And in turn, the third term would be 2 times the second term plus 1. So that would be 2 times k plus 1 plus 1. Expanding this, I'll have 2 times quantity of 2k plus 2 plus 1. And finally expanding that again, we'll have 4k plus 6. Now, we know that this third term is a positive integer between 1 and 2020 inclusive. So we can set that 4k plus 6 is less than or equal to 2020. Now let's solve this inequality. So again, we can subtract 6 from both sides. So we'll have 4k is less than or equal to 2014. Now next I could divide both sides by 4, which leaves me with k is less than or equal to 1007 over 2. And we want the closest integer to this because the k can only be an integer. And 1007 over 2 evaluates to 503.5. And we also have that k has to be greater than or equal to 1. since each term must be a positive integer as given in the question. Therefore, there are 503 possible first terms that will result in a sequence that we are looking for in this question. Now, do each of those possible first terms give a unique third term? And the answer is yes, because for every possible k value, first term k, we will have a unique third term 4k plus 6. So given a k, there is only one 4k plus 6, and two different k values will have different values for 4k plus 6. Therefore, we can argue that there are 503 possible third terms as well.